Okay, I will start my Tanner first. Then I will go for new design. I have already explained all this process in last class. If you have any problem, then please interrupt me in between. Okay. So I made the new design name as Cmos practice. I will add the library. This library is under Tanner tool only, the folder. So I will add library already selected. And then I will go for cell. I will the Cmos practice cell 0. Okay. So my cell is here. Cell 0 is here. Now what we will do? Now we will, my platform is ready. Now I will add devices. Anyone have any doubt in? Okay. So first of all, I will get my NMOS here. Done. Then I will get my PMOS here. Done. Okay. So my PMOS and NMOS is present. Now what we have to do? We have to connect the voltage source with that. Okay. So I will go to Spice element library. I will select voltage source. First, I will select one bitwise voltage source here. Bitwise. Okay. And we will name it as V in. Okay, leave it right now like this. Okay, this is done. Voltage source. Now, okay, we need one more voltage source for VDS. Okay, so this is VDS and this is VGS. So what else we need? We need one ground also. We are connecting voltage source, so we have to connect ground also. So under mixed library, we will get ground. We will take this ground and we will give it here. Okay. What else we need? We need one output port also from where we will see the output. So we are giving one port. This port is of size 8 and its name is output. Whatever the name you want to, you can change it to. Okay. It is very useful thing. You will see how we will use this thing. Port. Okay. So now what we have to do? We have to connect. Okay. So I have selected wire and I'm connecting this and this. And this is the bulk of NMOS. The bulk of NMOS is connected to ground, means to the source. Okay, and this also goes to the PMOS. Means PMOS NMOS connected should be connected. Okay, so and this side will we have to connect this one, and this is the bulk of PMOS, and it will be connected to the drain. Okay, of PMOS. Now this PMOS will be connected to VDS, which is a 5 volt. VDS is also connected to the ground. And this output port, from here we usually see the output in CMOS inverter. So this is my output. So I have connected it to the output port. Okay, so this is our design. And what we need one measurement of print voltage. Means we are going to observe our voltage, input and output voltage both. So I have connected one print voltage from input side and print voltage from output side. Okay. Next, we will perform the simulation. First, we will check whether our circuit is correct or not. So as you can see, our circuit is correct. Zero error. One warning is there. So that's not a problem. And this is my bit input. Okay. And its pattern is like, I will show you the pattern. You can see here the pattern on right hand side. The pattern is like 0, 1, 0, 0, 1, 0, 1. I will make this one as 0, again 1 and 0. Okay. So this is the pattern. And next what we have to do, and this is where this is VDS. So this is print voltage This is in transient, no problem. The sprint voltage, this is also in transient, no problem. Right now, we will do the transient analysis, first of all. And so we are giving input in the form of bit 0, 1, 1, 0 like that. So we should expect the output opposite of the input pattern. Then we will confirm that our CMOS inverter is working. Got it? So I will go to the simulation part. I will add the library path here. All these things, how to add, where we will see, find this technology file of library. All these things have already explained in your last class. Okay. So vice element, we don't need all these things right now. We are going for the transient analysis. So we will just click on DC operating point, and then we will come to transient Fourier analysis. We will keep the 100 nanosecond as the stop time, and maximum step time should be 10 nanoseconds. Okay. So nothing else we don't need right now. We click OK. So our settings parameter is already done. So now we will run the simulation from here. Okay, so I will change this graph. I will take this. When you will click on this button here on above, then this graph will be separated. Means input output graph is on same axis right now. We can separate this by clicking here. Okay, so I have separated this. As you can see, my input is on above. This is the red one. This is the input, and below one is the output. As you can see, when I will take my cursor here, exactly at above, you can see the traces, means the x-axis and y-axis. Are you getting, guys? Please, someone reply.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes,
Okay.
sir.
So you can see the traces here. When I take my cursor here, this is 11 nanosecond on 11 nanosecond and on 5. Okay. You can check this. You can check this here also. It will come here above also. Then I will take my cursor here. You can see exactly the point. Okay. Exact point above also. Here also, this starts from almost 10 nanosecond and it goes to 11 nanosecond. Okay. So this is our rise time. And if we will see the rise and fall time at output, same thing happens. The output changes when this is going for 0 to 1, my output is going from 1 to 0. So my inverter is working fine. No problem with the inverter. But here we have to consider the rise and fall time. Okay, guys? Because when we are going to develop further circuits using this CMOS inverter, because in future practicals we are going to develop NAND gate, NOR gate, we are going to make some flip-flops with this or carry adder with this. So these things will affect in those circuits. This rise time, fall time, duty cycles, all these things you have to take into consideration whether it is in nanosecond or what. Okay, because when you will implement 4 inverters, then this rise time, fall time will keep on adding, and it will eventually affect the overall circuit. Okay, in future. So you have to consider this rise time, fall time, charging time, discharging time, all these things. Okay. Okay, so right now you can see my output goes from 10 to 11 nanosecond, and this is my rise time. And my fall time, input. And my fall time goes from, this is 20 nanosecond, and here it is 21 nanosecond. So 1 second rise time and 1 second fall time. What happens in our output side? See, this is 10.94. This is 10.94 seconds. It starts with 10 seconds and it fall time will be 10.94 seconds. So my fall time at output side is 0.94 seconds, nanosecond, sorry. Okay. And the output and the rise time will be, see, it starts with 20 nanosecond and it goes till here. So it goes to 21.25 nanosecond. So my rise time at output side is 0.25 sorry, 21.25 minus 20. So it is 1.25 nanoseconds. Okay. So it taking more time. Okay. If you will compare with the input, my input comes from 1 to 0 in 1 second, but at the same time, my output goes from 0 to 1, taking 1.25 seconds. Okay, so this is because of the internal resistance of NMOS and PMOS. Have you studied this, the formula of resistance of internal resistance of NMOS and PMOS in devices? Have you studied electronics devices, semiconductor devices and circuits? Anyone? Please reply something, guys. Yes or no, or don't remember something, some
Sir,
input.
don't remember, sir.
Okay,
Yeah,
fine.
Nara, sir.
Okay, so if you are not remembering, then I should remind you. So this is because of the internal resistance. You know the rise time, fall time, all these things depends on RC. Okay, resistance into capacitance. इतना तो formula याद होगा.
Yes, sir.
So this resistance is what is the internal resistance of NMOS and PMOS. Got it? They have internal resistance. और कैपेसिटेंस अगर हम लोग कोई कैपेसिटर लगा देते हैं तो वो कैपेसिटेंस होगा मींस इफ आई एम गिविंग सम कैपेसिटर एट लोड साइड मींस दिस साइड एट आउटपुट साइड then that capacitance, there are some wire capacitance, there are some diffusion capacitance in this PMOS and NMOS also. Okay, there are some drift capacitance. So these capacitance get added up, and the resistance, internal resistance of PMOS and NMOS, all these things get added up, and in combination they will this timing of device, this overall CMOS, it depends on this resistance and capacitance. This is what happens actually. Okay, see, I will give you one example. Like if I will attach one capacitance here at output side, I'm going to attach one capacitor here at output. Okay, see, this is the real-time analysis of the circuit. What you have learned in your theory classes, you can directly implement these things in here, and you can see the result, and you can search for the reasons why this is happening. Okay, or you can ask us. So you can see this capacitance. I have attached one capacitance at the load side, and its value is 1 picofarad. Can anyone tell me the pico means? What is the value of pico?
Sir, 10 to the power minus 12.
Okay. So if I will make it as if I will make it as 1 nanofarad, sorry, 1 nanofarad. So I am increasing the capacitance. Am I right?
Yes, sir.
Okay. So on 1 nanofarad, I will check what happens to our circuit. See what happens. My output is get distorted. Okay, it's changing its due course from 0, but it doesn't reach 0. It assuming that this 4.9 is 0, and again it discharging, and then assuming some values, then it's discharging. Okay, this is what happens when we will put uncalculated capacitance at output. If I will make it as 1 picofarad only, then see what happens. If I will keep it as 1 picofarad only as the default value, then see what happens. Again, our charging and discharging time changes, as you can see, guys.
Yes, sir.
See, here my fall time becomes 13.84. It starts from 10 and it falling till 13.84. So my fall time becomes 3.84 nanoseconds. Are you getting? And here, if we will see the rise time, then it starts with 20 and it goes till almost 29.04. So it becomes 9 nanoseconds. It is a huge difference. Are you getting? So we can, by changing the value of capacitor, we can change this rise and fall time also. This is one way of doing it. Okay. See, if I will change the value of capacitor from 1 picofarad to 0.1 picofarad, and I will close this one, close this one. See, you have to go through your theory notes or books, previous notes, some devices, and you have to check the all these parameters value, how it changes. So guys, you can see here, my rise and fall time changes. Okay, this is quite good. My here my rise time almost come to 1.5 nanoseconds. Before it was 9 nanoseconds. So this is how we can control the rise and fall time. And there is one more process with that we can use. One more process we can use. This is using the capacitance. Okay, delete this one. And the second process using resistance. How this resistance we can change? By changing the W and L ratio of PMOS and NMOS. Because if you will see the formula of current of PMOS and NMOS, then it's depend on W by L ratio of PMOS and NMOS. W by L ratio means width and length. Okay. So what I will do here, I will just first, you can see the width is 2.5 micrometer and length is 0.25 micrometer. So what we will do here, I will change this W by L ratio. Right now my W by L ratio is 10. Okay. So I want to make it as 20. If I will make it as 20, what will happen? We will see. So if I will keep this W on 5 micrometer, then the ratio will become 20. So my W is on 5 and L is on 0.25. And I am not changing anything in NMOS. NMOS, I am keeping it as it is. So after this, I will check my output. Can I see any changes here? And this becomes 10.88. So very minute changes in fall time, very minute. Okay, first of all, it was 10.94 and now it becomes 10.88. Okay, so very minute changes. And here, if we will see in rise time, what happens in rise time? Now it is 20.87. Before it was 21.5. Now it is 20.87. So we have reduced the rise and fall time. We can see because I have changed the W by L ratio of PMOS, and by changing W by L ratio, my current changes, and by current, my resistance changes. You know the Ohm's law. Okay. So the internal resistance got decreased. So my rise and fall time increases. Got it? This is how we will vary this W by L ratio of PMOS and NMOS every time whenever we will stuck with the charging and discharging time. Got it? Because this is pull down transistor. PMOS is also called as pull down transistor and NMOS is also called as pull up transistor. NMOS will always go for making this overall circuit as on, means it will always go for 1, and PMOS will be always going for 0. It will make circuit 0. Okay, that's why it's called as pull down transistor, and this NMOS is called as pull up transistor in this CMOS circuit. Okay, I will show you how we can see that thing also. So everyone got it till here? Any problem? Please reply.
No, sir.
Okay, so please mind it, guys, because in future I will give you some assignments, I will give you some tasks in which you are required to observe this charging and discharging time, everything, and then only if you will not calculate this charging and discharging time properly, then you can't able to build that circuit. If we will go for carry adder, full adder, ripple carry adder, in those circuits, you need to see the charging and discharging time. Otherwise, you will not get the output correctly. Okay. So now we will go for next thing, VTC curve. Okay, DC analysis. Okay. This was the your transient analysis. Now we are going for transfer characteristics. Okay. For that, I will change this voltage source from bit. It is on bit. Sorry, not this. Yeah, yeah. This is on bit right now. I will change it to DC value, normal DC value, and now I will make it as a parameter. I will make this one as and I will give its name as VGS. Okay. So V input is our VGS, and I will keep this as VDS as 5 volt only. This one. I don't need this one to change, to vary. That's why I'm not changing this one. I need to vary VGS only. That's why I'm changing this one. I'm giving its name something. So I have to change this print voltage command also because it is on transient right now. I have to make it on DC. Otherwise, it won't measure. So please mind these things, guys. Otherwise, you won't get the output. I have to make this print voltage also from transient to DC because we are going for DC analysis right now. My input is DC. My output should be also DC. So in settings, I have to give parameter here. I will make this parameter name as the name I have given to our input side, that is VDS, and the value should be 5 volt. I will keep it as 5 volt maximum value. Now the parameter is already done. Then I will go for DC sweep analysis. Okay, because I have to sweep this parameter VGS. Okay, I have to sweep this parameter from source parameter name is VGS. Same name I have to give. The start value will be and when start value will be 0, top value will be 5, and the step means the increment value will be 0.5. Okay, and it will go linearly from 0 to 5 in 0.55 steps. So DC sweep is already there. I have fixed it. Parameter I have given. Okay, everything else will be same as it was. Okay, so nothing else. Now click OK. And first of all, I will make this Cmos W by L same as it was before, as it was on default value. It was 2.5 before, 0.5 micrometer. So it is W by L is 10 right now. So PMOS is W by L is 10 and NMOS W by L is 10. Okay. So we will check the simulation result. Okay. Click on this. Okay. So you can see the simulation result. This is the discharging. Okay. This upper half is because of NMOS. You can see in the output in this green one. This is just your input VGS. It is linearly increasing. Okay. And your DC operating, your Q point is at the crossing here. You can see, and it traces is at 1 point. You can see the traces. I will put one. Okay. If I will get the pointer here, above you can see above. See, it is 1.84 and 1.87. Okay. This side is because of NMOS and this side PMOS, and this side is because of NMOS. Okay, charging and discharging, you can see. So what we need right now, we need both of this upper half and lower half. This Q point should be in middle. Okay, should be in middle. So what is the middle point of this graph? Anyone? Can you tell me X and Y? What is the middle point? What is our desired Q point?
So 2.5.
50% of VDD.
50%. What is 50%? Tell me the value.
2.5.
2.5 x-axis and 2.5 y-axis. Okay. See, if I will reduce this graph, you can see this is not on the middle side. Okay. If this output will cross here somewhere like this, then I will get the middle one. Okay. So if I will change, I will not save this one. If I will change right now I will change my PMOS from 2.5 to 5 micrometer. And again, I will check the output. What happens? You can see. I'm changing my W by L ratio of PMOS from 10 to 20. Okay. So it is 2.41. You can see this is almost correct.
Yes, sir.
Almost correct. We are getting. ठीक है ना? तो यही चीज हम लोगों का डिजायर्ड है. ओके. This is how we will check the output. We will check our Q point, everything. This is our desired output. अगर ये हम लोगों को मिल जाता है almost in the middle, then we can proceed for our further circuits. This is what we need. Okay. So you people have to also do this, and I will suggest you do one thing, means change the parameters, means W by L ratio of PMOS, and check the output. And after changing PMOS, go for NMOS W by L ratio also, and try to change this one also and see the variation in the circuit. You will find the very good and nicely charging and discharging results. Okay, this VTC graph will change. Then you will understand what's happening by changing W by L ratio. Everything from now on will depend on this W by L ratio. I'm telling you. So don't ignore this. Try to perform this very nicely. Each and every step, take the output waveform screenshot and save it of each and every W by L ratio. Write it down. Make a table. Okay, write it down. That PMOS is right now W by L ratio is this, NMOS W by L ratio is this, and at this W by L ratio, what output you are getting. Save that output, and again change this W by L ratio, and check the Q point measurement also of that output, and write it down. So in tabular form, write it down. Means in one column make PMOS W by L ratio, in second column make NMOS W by L ratio, and in third column Q point. Okay, and each and every W by L ratio you have to vary these W by L ratio, and you have to see the Q point. Okay, then you will understand what is happening. No doubt. So this is your second experiment.